Check it out now, y'all.
NanoHub U, online instruction.
Well, welcome back. We're starting a new week, and we're going to move into 2 and 3 dimensions and discuss Schrödinger's equation for some problems associated with these added dimensionalities, and we'll see what new features come out of the solution of Schrödinger's equation. So by way of introduction, it's probably useful to review some of the things that we've already learned or discussed. And in particular, what I like to do is I like to focus on the wave function, right? And I like to just have a general discussion of that wave function and just basically point out that if we know the wave function in quantum mechanics, in principle, we know everything there is to know about the system. It's just a question of calculating the eigenvalues of various operators that are defined for a system of interest. And the point I like to make in this slide is that the wave function has to depend on the coordinates of all the particles that are involved in the quantum system of interest. And I just illustrate that by listing a few different scenarios and then listing the appropriate wave function for each scenario. So up until now, most of our discussion, we've worried about just one particle in one dimension, and the wave function has been referred to as psi as a function of x. If that single particle is moving in one dimension, okay, if the particle has a time-dependent property, then the wave function has to include both the position x and the time t. So the first wave function is referred to as a stationary state of the system because it's independent of time. The second wave function is useful for calculating how the system changes with time. That is not so much a concern in this course, although in a couple of weeks we will do some time-dependent calculations just to give you a flavor of what's going on. Perhaps the most interesting aspect of quantum mechanics, the feature that distinguishes it from classical mechanics, is that if you have a particle in the system and you don't know what state it's in, let's say it could be in state A or state B, then you have to write what's referred to as a state wave vector, which is the linear combination of the wave function for the particle to be in state A plus the wave function for the particle to be in state B. The relative coefficients A and B that are used to define this state vector, these coefficients then tell you the probability that you find a particle in state A or the probability that you find a particle in state B. So this is a new feature that quantum mechanics allows that's not possible in classical mechanics. The other wave function, the other form of the wave function I like to emphasize is that if the particle is moving in 3 dimensions, then what we're going to have to do is we're going to have to write a wave function that depends on the vector position r of the particle, right, which is going to have a component in x, a component in y, and a component in z. So a lot of the next 2 lectures are going to focus, or actually all the lectures this week are going to focus on the vector r, where the first case we consider r is going to be in a 2-dimensional plane, and then when we talk about atomic hydrogen, r will be a 3-dimensional vector. So it's important for you to start to appreciate the subtleties of these different forms of the wave function because they tell you about the problem that you're trying to solve. The other thing that we spend a fair amount of time on is the mathematics behind the Fourier transform integral. So this Fourier transform integral allows you to take a wave function in real space and write a wave function in k-space or vice versa. I think the time we spent is justified because the mathematics behind this Fourier integral is so ubiquitous. It's everywhere in engineering and science. And so the more you know about how to handle these integrals, I think the better off you'll be as your studies progress. So this is another thing that we've emphasized quite a bit. And Just wanted to remind you of that fact. The topic of this lecture, though, is going to be what happens if you take a particle of mass m sub e and you drop it into a rigid two-dimensional potential well. So what do I mean by that? I mean that there's a region in space that's a distance L in x and a distance L in y. So it's a square region in space. And we're going to say that the potential energy of the particle inside that region of space is equal to 0, independent of x and y coordinates. And once x gets greater than L, or once y gets greater than L in the y direction, we're going to say that the potential energy of the particle goes to infinity. And this just means that there's a rigid box that the particle is free to bounce around in. The dimensions of the box are L by L. And we want to know quantum mechanically what the predictions of the energy eigenvalues are for the particle when it's trapped in that two-dimensional potential well. So how do we solve that problem in quantum mechanics? Well, we just take Schrödinger's equation in one dimension and we extend it to two in a very straightforward fashion. We now include a second derivative with respect to y, in addition to the second derivative with respect to x that we've dealt with for the past few weeks. We add in the interaction potential energy U, and we set that equal to the total energy E of the particle times the wave function psi. So it's the standard eigenvalue problem that we've already discussed. Except now we're talking about two-dimensional situation. The problem is greatly simplified if we set the interaction potential energy U equal to 0 when the particle's inside the box, and that allows us to simplify Schrödinger's equation in two dimensions into this rather simple form, which says that the second derivative of the wave function with respect to x plus the second derivative of the wave function with respect to y is equal to constants, fundamental constants related to the problem, times the energy eigenvalue E times the wave function psi back again. And now the trick is going to be to find out what that wave function is. Probably there's no simple way to describe a systematic way to find the wave function for this differential equation. What you basically have to sit down and do is try a few combinations, a few simple ideas about what psi should be, and then see what the consequences of those guesses are. The actual solution is given by a product of two wave functions. One is a wave function only of x, the other is a wave function only of y, and you multiply capital X times capital Y, and you say that's equal to the wave function psi that satisfies this differential equation. So the question then becomes, does this guess for a wave function, what are the predictions for that guess? Does it in fact satisfy Schrödinger's equation? And what's the systematics behind that guess? So this is referred to, this type of wave function is referred to as a wave function in which the variables are separated. The two variables here are x and y, and what we're postulating is that the wave function, the actual wave function psi, is a product of two functions, one a function only of x and the other a function only of y. Now, the virtue of that guess is immediately shown when you try to evaluate the second derivatives that appear in Schrödinger's equation. Since only the second derivative with respect to x appears, when you operate on this wave function psi, the capital Y component of the wave function just goes through the derivative untouched because we're taking the second derivative with respect to x here. And so we're left with a term that says the second derivative with respect to x of capital X times the component capital Y, right? That has to then go into this spot in Schrödinger's equation. And a similar thing happens when you take the second derivative of the wave function psi with respect to y, right? The x component of the wave function just filters through the derivative, right? We're left with the second derivative of capital Y with respect to y squared, right? In addition, the partial derivatives that act on psi here get turned into total derivatives because now this function capital X only depends on X. This function capital Y only depends on Y. So you can replace the partial derivatives by total derivatives without any loss of generality. Schrödinger's equation then becomes an equation that looks like this. If you make the substitutions in for the second derivatives of psi with respect to x, second derivative of psi with respect to y, you're left with an equation that resembles this. And if you then divide through by the wave function psi, you're left with a term that depends only on x, that's indicated by red, and then there's a second term that depends only on y. Now, this is a very interesting form for a differential equation because it says this first term, which depends only on x, is added to the second term, which depends only on y, and that's equal to a constant. The constant is these 2m over h bar squared. Those are the fundamental constants of the problem, times the energy eigenvalue E. And that has to be true for any x and y inside that potential well. Well, that's kind of strange equation to deal with because this term here, the first term that depends on x, could be very complicated. And likewise, the second term that depends only on y could be very complicated. And you have to ask yourself, what are the chances that when you add this term that depends only on y to this term that depends only on x, how can it be that the sum of these two things is always equal to the same value, independent of x and y? That's a very strange situation. And what it leads to the conclusion is that this first term is a constant, this second term is a constant, and that constant is given the symbol case of x squared and case of y squared. So the only way this equation can be true for any value of x and y is if the first term is equal to some constant, second term is equal to some constant, then you've just got the sum of two constants equals a constant, which is, of course, completely reasonable. So this complicated differential equation with a little bit of thought then breaks down into two simpler differential equations, which I list in the yellow box. And these two separate differential equations are exactly equivalent to Schrödinger's equation with this hypothesis that the wave function is the product of a function only of x times a function only of y, right? And so now we're left to solving these two differential equations, which are a lot easier to deal with than this equation here. So there are various things we have to deal with if we try to find solutions for these two differential equations. One issue is the boundary conditions. The boundary conditions insist that the wave function has to go to 0 when x is equal to 0 and when x is equal to capital L. Likewise, the wave function has to go to 0 when y is equal to 0 and y is equal to capital L. This is because the potential barrier is infinitely high at those two limits. And so with those boundary conditions, an obvious suggestion for a solution is a sine wave. And so we postulate solutions that look like sine of kx and sine of ky times y, right? So these are the two solutions that match these boundary conditions. And to make the boundary conditions precisely true, the constants case of x and case of y have to be quantized, right? And they have to be quantized such that an integer n times pi over L is equal to k sub x. Another integer m times pi over L is equal to k sub y. And the integer n is 1, 2, 3. The integer m is 1, 2, 3. And the values of n and m are completely arbitrary at this point, right? They can be chosen independently of one another. So notice that the quantum number m in this problem does not have the subscript e associated with it. So the mass of the particle is subscripted with e, basically to represent the mass of an electron. The quantum number m is just given as an unsubscripted number, so that allows you to distinguish between the two variables. So with this discussion, we then have a solution for Schrödinger's equation. It's a function only of x times a function only of y. The function is the function that only depends on x is a sine function. The function that only depends on y is also a sine function. The argument of the sine function should be familiar to you from our prior discussion. And the key feature here is that there are now two integers, n and m, that come into the discussion. With this form of the wave function, it's then possible to go back and evaluate what the eigenenergies are. And that just simply comes about by taking the second derivative with respect to x and the second derivative with respect to y of that wave function that we wrote down on the previous slide. And when you do that, right, you get the argument of the sine function squared that come through. You can then divide both sides of the equation by the wave function, and you're left with an equation that I write down in the yellow box, which says what the allowed energies are, right? The allowed energies depend on the constants of the system, so they depend on h bar, the mass of the particle, m sub e, the size of the box, L, times the square of n plus the square of m, where n and m are the two integer numbers that are required to match boundary conditions for the problem. So this is kind of interesting because it basically allows us to make a table of the allowed energies of the system, right? So if we represent all these constants by some quantity E0, then the allowed energies are E0 times the sum of n squared plus m squared. And what we can then do is we can create a table that we pick possible values of n, possible values of m, and evaluate what the total energy of the system is, right? So we have to start with n equals 1, m equals 1. It's not possible to have n equals 0 or m equals 0 because those choices don't satisfy boundary conditions. So it's important to realize that the range of the quantum numbers depends on each system that you consider. So in this case, it's not possible to have n and m start from 0, n and m have to start from 1. And that implies that the lowest energy that the particle can have in this system is equal to 2E0, and of course you get that by putting n and m into this equation. When we get to the next highest energy state, so we're going from low energies up to higher energies, right? As we go to higher energies, n can be 1 and m can be 2, or n can be 2, m can be 1. Both sets of quantum numbers give us an energy eigenvalue equal to 5E0. And we run into this situation, which is the first time we've really seen it this semester, where we've got two different quantum states with different quantum numbers that give us the same energy eigenvalue. And this just simply means that this state at 5E0 is twofold degenerate, which basically means that there are two separate quantum states that give you the same energy eigenvalue. So this degeneracy idea is going to come and play a more prominent role as the semester advances. This is the first instance where we found a state which is actually twofold degenerate. The next highest energy comes in at 80, 0, and that's given by choosing n and m equal to 2. And, you can just fill out this table and calculate all the possible energy eigenvalues that this particle can have when it's dropped into this two-dimensional potential well. It's kind of interesting to plot psi star psi for these different energy eigenvalues, try to get a sense of what the quantum state looks like. So as you recall, psi star psi is the probability density of finding a particle in a distance dx if the problem is one-dimensional. In this case, the problem is two-dimensional, so psi star psi times interval dx times dy is going to tell you that the probability tell you what the probability is that you'll find a particle in a small box located inside the potential well, which has got a unit, which has got a length L in the x direction, a length L in the y direction. So here I just plot psi star psi. Here I pick the quantum number n equals 1, m equals 1. This is for the energy eigenvalue of 2e0. And white color indicates a high probability. Dark black color indicates a low probability of finding the particle in those regions of space. And so you can see that this lowest energy eigenvalue gives you a particle which is localized in the center of the box, and the probability of finding the particle as you get to the edges of the box drops off significantly, goes to 0 in fact. There are other energy eigenvalues that you can plot. I just do a couple of examples. So this is what you get when you take the n equals 1, m equals 3 quantum state. The energy eigenvalue for this state is 10e0. And you can see that now you've got 3 lobes, right? So that if you did many, many experiments and you grabbed the particle from the box and you plotted the probability of finding the particle at different positions in the box, you would find that more often than not, the particle would be found in either one of these 3 lobes of the wave function, right? Again, the probability goes to 0 as you get toward the edges of the box in order to match the boundary conditions. You can render these plots in 3 dimensions. Sometimes you'll see different versions of the plots, right? So this is the same case, n equals 2, m equals 3 quantum state. In this case, there are now 6 lobes where the probability of finding the electron is very high. This is the false color plot with contours. This is a 3-dimensional rendering of the same plot and shows you that the probability of finding the particle in these various regions peak up. They have a high value. So that's what the wave function means. That's what it means. That's how you interpret what it means in terms of wave function times its complex conjugate. The other thing that's interesting to do is to start to make plots of the energy eigenvalues for the different quantum numbers that we've chosen. And there are 2 ways to do this, and it's important to understand both ways. One way to do it is to just plot the energy eigenvalue versus energy. And so each energy level is then labeled by a quantum number. And you can see that some of the energy eigenvalues are doubly degenerate, right? So there's exactly 2 energy levels at an energy of 5e0, whereas when you go to 8e0, there's only 1 energy level. So this is a plot of the energy level versus quantum numbers, right? The other way to do this is to plot the allowed energy eigenstates as a function of kx and ky. So remember, kx and ky have to be quantized in order to match the boundary condition. They're quantized in terms of integers n and m. And so now you can take each of these states and you can plot them in terms of their allowed kx, ky values. So for instance, this state here at energy 2e0 shows up when kx is equal to pi over L, ky is equal to pi over L. There's 1 state at that energy, and that's indicated by this red dot. This blue energy state here is doubly degenerate, and that shows up because there's a state at kx equals 2 pi over L, and ky is equal to pi over L. But there's an equivalent state with the same energy when kx is equal to pi over L, ky is equal to 2 pi over L. So these blue dots correspond to the two energy eigenvalues that are listed on this plot. Right? So this is another way to visualize these quantum states. How would you check whether this calculation is realistic or not? There's a simple way to do it. The simple way to do it is to cause the particle to be excited from its ground state up to some higher energy state, and then watch what happens as that particle decays back to its ground state energy, right? So based on what we've already discussed, if you've got a particle in a quantum state, it can make transitions, right, to other quantum states at lower energies, and these various transmissions will emit photons. So just by measuring the light that comes out of this system after it's been excited, right, you can start to predict energy spectrum, or the spectral distribution of light that comes out in terms of the predicted energy levels of these particles. So this assumes that these transitions would emit radiation. We have to think about that in a little bit more detail, and we'll do that in a few weeks, try to clarify that issue. But if these are radiative transitions, if photons are emitted when an electron jumps from one energy level to another, then you can start to predict this energy spectrum. And if you then measure the emitted light, you can compare that spectral measurement back to the original definitions for the particles' energies. It's a fair question to ask whether this type of a system of a two-dimensional box with infinitely high potential barriers, whether that's a realistic approximation. And so I'm just looking in the literature, looking for situations where you have very thin plates in one dimension, but they have large extents in the other two directions, X and Y. What I found is these FinFETs that Intel is now touting for their new transistor geometries, right? These FinFETs are very narrow in one dimension. They apparently have larger dimensions in the other two directions. So possibly the electron states that are trapped inside this narrow plate can be well approximated by these simple models for two-dimensional electrons, or for electrons trapped in a two-dimensional potential well. So I just mentioned that. It's an interesting development, and we have to talk to some of the experts at Intel to find out if the electron states along this direction are in fact governed by these quantum states that we've just calculated. So I'm running a little bit over, so I have to wrap this lecture up. I'll just say that the next lecture we're going to focus on counting the quantum states in this two-dimensional potential well. So when you come back and listen to that lecture, we'll describe a simple way to enumerate those states, and it's an idea that we're going to use later in the semester. When we use it again, it's going to be a little bit more complicated. So it's important to understand the basic ideas now when we've got a simple toy system to think about. So see you in the next lecture. Thank you.